all of you. What do you think philosophers can contribute to the debates that are taking place in the field of quantum thermodynamics and quantum information?
Who wants first? Let me think. So, I mean, what I already found interesting was, for example, in Wayne's talk, to hear that some of these ideas have already been there 100 years ago, that you should think of thermodynamics as some kind of control theory or something like this. So it would be helpful, I think, to maybe compare this as well, see whether it's really just the same ideas, just in different disguise, or whether there are really things we do differently, or if we can really learn something from the ideas people had back then on that. So that's something that I found really interesting here on the first day. I would have to think more about this question. I mean, you gave us also a bit of food of thought for that, I guess. Right. Do you have a suggestion? Just to give the question back.
I mean, I think one of the goals of philosophy of physics is also to clarify certain concepts that are being used, and to pull things apart that might be mixed together. Mm-hmm. But I always wonder whether physicists consider this actually helpful for their day-to-day work.
Well, I wouldn't mind too much, because some physicists will always find it unhelpful. But I would find it interesting, because we tend, obviously, to put questions under the rug that are kind of obvious when you do these kind of approaches. Of course, we can do proofs about catalysis and whatnot and transformations for probability distributions, for example. But you could ask, what do these probability distributions mean? How would you really deal with them in practice? Is the catalyst, is it really a box that contains some of your ignorance? So, or is it a mechanical part of a machine or so? So I personally would find it interesting to have this more fleshed out, which is something we never do, obviously, because we're just very busy with proving theoretical results on it. Yeah.
So one way of characterizing a lot of what I've been hearing in this conference about these sort of approaches to thermodynamics is there are ways of going beyond the just straightforward sort of inequality way of writing, expected value inequality way of writing down the second law, and in particular going beyond it in analysis of small systems. So as you all know, as many people here know, one of the other sort of really interesting developments in thermodynamics recently has been the kind of Krug's-Jablonski style way of going to sort of equalities that govern second law and indeed testing those things in small systems. Are there connections between these two sorts of approaches that I ought to be making?
Yes, definitely. Maybe actually you know more about this.
Yeah, exactly, because Jonathan had some work on, for instance, and other people, of course, Aber, for instance, on like studying fluctuation work in the framework of resource theory. And I think something that I find personally very interesting is that because of the fact that there is a common structure between many different resource theories, then being able to find some result in one resource theory very often give you the possibility to extend to other one. And in fact, since majorization plays a big role within thermodynamics and entanglement theory for pure state, something I know is that the same kind of fluctuation theorem that people had for thermodynamics they have been extended to entanglement, for example, which I think is something very interesting. And I think also for coherence, for the resource theory of coherence. That's another framework where I heard they've been extended this way. I don't know.
I also think there's a work where instead of the expectation value of e to the minus beta times, well, the usual thing you have in the Jablonski relation, you look at some kind of worst case or scenario instead of the average. Things like this, but I'm not very familiar with these papers. But there have been a couple of them just in the last 2 years. So Nicole Junger-Halpern is one of the authors that come to my mind. Yeah. But if you like, we can look up the paper. So.
I was really, really pleased on behalf of James Clerk Maxwell to hear Nellie saying that when you get down to the micro level, the distinction between work and heat tends to be unclear, because he would be very, very thrilled to hear that physicists in the 21st century are saying that. On the other hand, as I emphasized in the talk, thermodynamics originally is the science of the interconversion of work and heat, and requires a clear distinction. So I wonder, and both Maxwell and Gibbs thought that the province of thermodynamics was this large ending regime where where fluctuations can be ignored. So I like your idea. So there's two attitudes you can take on this. One might be, well, when we get down to the micro level, this distinction between work and heat, it becomes unclear, and maybe we should stop trying to apply thermodynamic concepts at that level, and just do statistical mechanics, either quantum or classical. And I suspect that's what Gibbs would have said. But the prevailing attitude tends to be, well, actually, what we find is something a lot more interesting. We can extend thermodynamic concepts to that level, but they multiply. Things that become the same in the large N limit have multiple realizations, right? Which also gives is a remark that Gibbs made. So I guess this isn't a question, but any thoughts on those two kinds of attitudes one might take towards this kind of work?
Well, I think that some people do feel that if you are looking at this miniature heat engines and you extract a small amount of work, what does it even... It's not useful for anything in some sense. And thermodynamics has always been kind of fueled by this very pragmatist perspective that we want to achieve something, and we kind of describe our system so that we learn how much we can achieve. And this goal is something that we have already said that this is meaningful, I want this. But then work or like highly ordered energy might not be exactly what it might not be exactly what we want in quantum thermal. Nevertheless, I think that there are still potential candidates of things that we want. For example, I talked about initialization, and that has become very important in quantum computation. They do really want, as someone told me yesterday, to initialize states up to 99.99 something % of fidelity. And they do want that kind of accuracy. And how can we kind of design the thermal machines, maybe not to extract work, not necessarily, but how to initialize states, how to prepare states with very, very high precision, and how to perform gates with very, very high precision. And that will be very important for quantum computing one day, I think. So,
I would also guess you cannot really take the route of saying, oh, let's just not apply thermodynamics to these small systems and just drop it and do something else, because ultimately everything you find in the world, as long as you can control it, you can put in contact with other thermodynamic systems. So I mean, that happened to black holes, for example. You can just argue that whatever you find in the world, you would not want to be able to use it somehow in a way with another thermodynamic system to act, for example, as a perpetuum mobile. But when you make this statement, you're always already extending thermodynamics somehow to something that includes that other system. And now that we think we can control these small systems and they are relevant in some regimes, and I guess there's simply no way then to have some kind of thermodynamic view on them.
That's a good answer.
So, correct me if I'm wrong, but most of the main results in all of your talks were for the case of time translation in invariant states. Like those are the main results. So all the sort of big results in the field of the resource theory of aethermality are really just classical results. You know, we're just thinking of quantum states that are diagonal, and in the subspaces we can do anything we want. So it just boils down to probability distribution. So this is really all classical for discrete systems that have some number of levels. So in my talk, I speculated that the place, there's something more to be done. The quantum stuff is when you have coherences. And I speculated that all that coherent stuff is just about time translation asymmetry. Just those properties and nothing more. And I'm just curious if you guys share that intuition, or you think that truly quantum stuff is going to be, like, do you have any intuitive sense of what the truly quantum stuff is going to look like? What it's going to be about?
I mean, I personally think that it is true. It will be about coherence in the energy eigenbase, and I don't think it will be anything more apart from that. And like my intuition is, I mean, it has been shown that if you have access to a very big coherent reservoir, then with the framework of a thermal operation, you're then able to, like, a big coherent reservoir is a big reference frame essentially. Then you go back and you're able to do all your transformation you want, mapping state from no coherence to coherence or otherwise, no? And so, like, by just giving this big coherent reservoir, which is related to, like, just the problem of asymmetry, it seems that you surpass this problem, no? And so it seems that it all boils down to the problem of adding coherence somehow.
Maybe based on my conjecture, I listened to that proposal, and it's sort of like saying, well, if I do asymmetry theory and I give myself access to an infinitely large reference frame, which doesn't degrade at all when I use it, then I've kind of destroyed all the interesting parts of the theory, because this is so powerful it allows me to do things. So that, I'm no longer studying the resource theory of asymmetry anymore when I do that. And so it seems to me like maybe all the interesting stuff will be seen when you don't do that.
Well, no, I didn't mean to say that that's the solution. Mine was just to say, well, that is somehow is some evidence that tell me, look, by giving you access to a coherence, by removing all these restriction that relates to coherence, I can now do everything. So, to me, it seems that coherence is the important thing now that we need to consider when we have to do this transformation between quantum states, not probability distribution, but quantum state. And so I do agree that I do agree with you that possibly we shouldn't add a coherence reservoir. But to me, that's an indication that the passage to the quantum case will include, well, will be based on accounting for asymmetry. So to me, essentially tell me that, yes, the quantum part will be coherence. At least this is how I see it. I don't know if it makes sense.
There are some cases where you can also study quantumness without coherence. For example, the size of the bath, they can sometimes be smaller if you allow for all unitaries rather than just the semi-classical ones. And this can become relevant when you look at the third law, for example, like how long does it take to do certain transformations. Well, I mean, it's a bit of a technical story, but there are few possibilities maybe to say something interesting without coherence. But I agree, it will mostly be about understanding coherence and what constraints it gives you, I guess.
This is a sort of observation in a slightly different direction. I was just thinking about it. picking up on Marcus's comment about how the universality of thermodynamics and the extension to black holes. And I think it's quite a nice wake-up call for people like me who ultimately are temperamentally inclined to think about physical theories as a first and foremost description of physical goings-on, of the kind of sense in which operationist considerations seem to be quite deeply built into physics here. So I mean, if I think about black hole thermodynamics, and I think, okay, suppose black holes had not turned out to remain here, suppose there hadn't been autonomous dynamics of black holes, then because the black hole is a zero temperature system, I can, as a practical matter in principle, I can use a black hole as just an arbitrarily useful thermal resource. I can violate Carnot inequalities with it. The fact that in some sort of transcendent sense I haven't violated those inequalities because all stuff going inside the black hole is kind of doing my entropy math is sort of neither here nor there from an operational point of view. So it would be kind of tempting, coming from a sort of realist, operationalist skeptic starting point, to run into those kind of arguments in the late 60s, early 70s and think, well, that just shows the minimum sort of operations thinking here. If it turns out you can violate Carnot inequalities with black holes, then great, that's a useful thing to have learned. And of course that turned out to be completely wrong. It turned out, really surprisingly, that black holes did behave like thermodynamic systems in just the right way to store all that stuff. And I think that's a really striking piece of history, I guess.
So there have been these discussions in the 60s that you can throw stuff into the black hole and then just get rid of your entropy, right?
Mm.
I just know this from later popular scientific accounts, but
I think so. I mean, the two bits of this, the bit that seems to get a lot of the attention, and I haven't looked at the history super carefully, I've looked at most of the contemporary stuff, but the discussions you tend to see popularised tend to be sort of about information theory. But there are also these discussions of what kind of operations you could do. So I think Garrosh has this example where if I've got a bucket full of heat, if I just lower that bucket of heat really, really, really slowly to the edge of the black hole and then empty it out, then I've converted the heat to work with arbitrarily high efficiency. And you can quantum mechanics will save you from that in one way or another. You can think of it saving you because ultimately when you lower the bar super close to the event horizon, it's being held up by the pressure of the Hawking radiation. Mm-hmm. You can also think about it in terms of what quantum mechanics says it's a minimum size the box can have, and either of these kind of conspire to give you back the Carnot limit. But again, that didn't have to be the case, and it's kind of striking that one could predict it was going to be the case just on the grounds that one didn't want to break the operational structure of thermodynamics.
Right.
Yes, that's why historically, and so I know that prior to Hawking's calculation, predicting Hawking radiation, people were pointing out formal analogies between certain facts about black holes and laws of thermodynamics. And Garrosh was also pointing out, oh, no, wait, we can't attribute a non-zero temperature to these things and coming up with these sort of things. So at the time where people were they saying, well, gee, we like, there's a suggestive, these analogies suggest we can treat black holes thermodynamically, but there must be a piece missing because we can't attribute non-zero temperature to them? Or were they saying these are reasons for not treating them thermodynamically?
I'm kind of not sure. I mean, Bekenstein is famously arguing that we really should go beyond the analogy and treat them as really thermodynamic on kind of consilience grounds of look at all these thermodynamic features, so would it make sense that they're really thermodynamic, but in particular on information theory grounds. But that you worry that the significance of that paper is signal boosted in hindsight because it gets cited and recited after Hawking radiation sort of retrospectively vindicated Bekenstein. I mean, my kind of suspicion is that I don't think there's a very long period of time between Bekenstein doing that work and Buddy and people working out the classical laws of thermodynamics and Zeldovich and then Hawking finding their way towards the fact that I have radiations. And given given this is the 70s, and so you haven't got really fast exchange of published information, I suspect to work out what's actually going on, you have to go to the sort of oral accounts slightly more to talk to people about what's going on in the conferences and workshops.
I don't know off the top of my head, but there's a good review article that Eric Curie showed me once. I think he read it and discovered. I could find it, dig it up. The Garrosh anecdote, I think that was actually, it wasn't a paper of Garrosh, I think it was it was a remark he made in a workshop.
I certainly see that as citation history. And I mean, when I was looking back on stuff, I was sort of intentionally doing, okay, never mind what history looks like, what should we be saying, given that we don't prove that expert? I think the history's what to be dug in there.
Well, there's no more questions. Maybe people are tired after three days of conferences to wrap up.
Thanks to
Okay, thank you everybody. Yes.